Another edition of the Pore Lab lecture series. We are very happy to welcome Marcio Carvalho today here. So Professor Marcio Carvalho has worked in microscale flow research for more than 20 years. He received his PhD in chemical engineering from the University of Minnesota in 1995. He worked as senior process development engineer at 3M and at Imation Corporation, both in the United States. And now he's a professor at the Department of Mechanical Engineering at Pontifícia Universidade Católica at Rio de Janeiro, Brazil. His research is focused on several aspects of coating processes, non-Newtonian fluid mechanics, microscale flow of motions, and flow in porous media. So Marcio, welcome to Pore Lab, and the floor is yours.
Okay, thank you, Marcel, for the invitation, and good afternoon for everyone. Let me share my screen. So can you see my screen already?
Yes, we see it well. You can just make it full screen maybe. Yeah, perfect.
Okay. So good afternoon. I'm going to talk about microscale flow of complex liquid in porous media. This is some of the research we've been doing, I would say probably in the last 2 or 3 years in this area. So our focus in porous media flow is associated with oil production. So typically when you're producing oil, you're injecting fluids from a series of wells, and hopefully this fluid is pushing the oil towards producing well. But this displacement process is typically done in a non-uniform way, both microscopically and microscopically. So on a reservoir scale, because of the difference in mobility between the injected fluid and the displaced fluid, typically the displacement front is not uniform. This flow is inherent unstable. But even in the area that was swept by the injecting fluid, there's still a certain amount of oil that's trapped by capillarity. And this is a microscale phenomena. So if you put a magnifying lens to see what's going on inside the porous media, you have the injected fluid. I apologize for some of the Portuguese in this figure here, but you have water, for example, displacing oil, and oil ganglia are going to be trapped by capillary pressure. So if you want to displace that oil ganglia, you need to have a pressure difference in the water phase larger than the capillary pressure that's holding this oil ganglia in place. So it's intrinsically a pore scale phenomenon. If you want to reduce this residual oil saturation, you need to unbalance this equation. So you can do that from both sides of the equation. You can lower the capillary pressure by, for example, changing the interfacial tension between water and oil, or you can increase the pressure difference in the water phase by injecting some type of complex fluid. So this is the goal of our research here in this area. So as I mentioned, the injection of complex fluid may change the residual oil saturation by playing on the two sides of that equation that I showed you before. So if you're injecting surfactant solution, you may reduce the interfacial tension between the two phases. Polymer solutions, emulsions, and foams will have the goal of changing the mobility of the water phase. So you're increasing the pressure difference that's acting in each oil ganglia. So the effectiveness of this process really depends on pore scale flow mechanism. And again, that's the focus of our research. So there's great potential to use microfluidics and pore scale model to try to understand the physical mechanism behind all these different processes, and such that you can optimize them. What is the optimum operating conditions in order to really minimize the residual oil saturation, or what's the formulation of these complex fluids that also will optimize the oil displacement. So I'm going to tell here three little stories of research we've been doing in the last few years. One is associated with the injection of emulsion or suspension of microcapsules. So here's just a small clip. Imagine if this is a microfluidic porous media, you have these oil drops or capsule flowing through the porous media. And the idea is to use these individual drops or capsule to block the water path. I'll go in detail on that. The second story is associated with foam. So how can you form foam inside a porous media, and how this foam can be used to change the mobility of a gas phase and then increase oil displacement. And the third story is associated with condensed gas production. So the first part of the talk is associated with the flow of suspension of microcapsule. This was a result of research from many individuals. So Rafael worked on his master's thesis doing confocal visualization on this flow. José Roca finished his PhD doing numerical modeling of a capsule flowing through a constricted passage. Mariano was a postdoc here. Now he's a professor in the south of Brazil. And Bruna also finished her PhD on this area of microcapsule production. So the basic idea, I apologize here for the subtitles are in Portuguese in this picture, but I think you can understand. The basic idea is that if you're injecting water inside the pore scale, water will create preferential path, leave oil ganglia. But now if I have something to block the water path, I'll divert water to oil containing pores. And then this way I'm going to reduce the remaining oil saturation. So we need to control the degree of blocking by controlling the size of these capsules. So you don't want to block the porous media completely, because you need to get these capsules inside the porous media, and also associated with the size of it in terms of pore throat distribution in the porous media and so on. So there's a lot of design that needs to be done in order to optimize this process. So the idea of using dispersed phase as a flow diverting agent is not new. So these are very old results from this paper from 1973 from Macroscopic. What they were doing here, this is a field test done by Chevron. So the continuous line is oil production. You can clearly see that the oil production is going down, is declining. At a certain point in one well, they start injecting oil in water emulsion. So basically dirty water with small oil drops. And then they continue to inject water after that slug of oil in water emulsion. And then you can clearly see that the oil production went up. And then as you continue to injecting water, the production starts to go down. But if you get the tendency of oil production that you had before injecting the emulsion, and now if you get the production after injecting the emulsion, you have all this extra volume of oil that was produced. So we've done a lot of work on studying injection of oil in water emulsion to displace oil. So here's just one summary of one of these experiments. This was a sandstone that was saturated with oil. We injected water, and the blue line is the oil production. So after approximately 5 pore volumes, we were not producing any oil. So we were injecting water and getting water on the other side. At a certain point, we inject oil in water emulsion. So basically the water with small oil drops. The red curve is the inlet pressure. You can see that as we start injecting emulsion, the pressure goes up, because now we need to force these oil drops flow through the pore throats. And then we stop injecting emulsion and go back injecting water. And then you can see that the injection pressure goes down and the oil production went up. So we went from an oil recovery of 33% to 40%. And after a second slug, we went up to 55%. So in order to really control this process, to get the desired increase in the oil production, you need to control both the size of the capsule and the resistance of the oil drop, and the resistance of the oil drop to flow through individual pore throats. Since you want stable emulsion, there's not much you can do with the interfacial properties of the oil in water interface, because you need to put surfactants to stabilize this emulsion. So the idea is that instead of using drops, what if we use a drop that has a very thin polymeric shell around it, so it's a capsule, such that we can control the rigidity of this capsule, so that we could create dispersed phase that is easier or harder to flow through the individual pore throats. So that's what we start doing. So the first challenge was to produce these capsules with basically it's a liquid phase with a polymeric phase around it. We produce these capsules using microfluidic technique that was described in this paper by the Harvard group. And the idea is that you form a double emulsion template. So you have an interface that we color with this yellowish color. You have a polymeric phase as a middle phase, and then you have an external phase. If you get everything right, you get this uniform dripping regime, and then you can control the size of these double emulsions. This polymeric phase will cross-link, and at the end, you get your capsule. We can control the rigidity of these capsules by controlling what polymer you're putting in as a shell and the degree of cross-linking of the shell. So if you want a very rigid shell, you can cross-link a lot this polymer. If you want a more soft, you don't cross-link as much. So here's just like a cell phone video of the production of these capsules. And in this case, the inner phase was colored with this red dye. It's just for visualization purpose. And then you can see that they're very monodispersed. And then we can control, I'll show next, we can control the size and then do experiments. So you collect them and then you just wait for the polymer to cross-link. So as I said, you have the injection of these three phases, and you have to have the flow rates of each of the phases inside an operability diagram, such that you get into this dripping regime where you're forming a single drop that's surrounded by a polymer phase. If you're outside this operating regime, you can go to flow rate states that's not, or flow states that's not desirable. For example, here, if the middle phase flow rate is too high, so you're injecting too much of that polymer solution, you start encapsulating more than one drop of the inner phase, and that's not what you want. So we need to be operating inside this operability diagram. So this was part of Bruna's PhD thesis, determining what are the production diagrams such that you can control the production of these capsules. And moreover, if you're inside the operability diagram, how can you control both the size of the capsule and the thickness of the shell? Because this is are the two important control parameters. We need to control the size of the capsule depending on the pore throat size, and we need to control the thickness of the shell because the rigidity of the capsule is associated with the cubic power of the thickness. So small changes in the thickness will have a big change on how rigid or how soft these capsules are. So here I'm just showing an example of this study that by increasing the outer phase flow rate, we can reduce the diameter of the capsule. And by changing the other flow rates, we can control the thickness of the capsules. So once we know how to make capsules of different diameter and different thickness, the question is, what's the flow resistance of these capsules going through individual pore throats? So what Bruna did was run experiments on a single pore throat model. So these are constricted capillaries where we have this constricted region. And then we're going to flow these suspension of these capsules through this constriction and measure the pressure drop. So we can see the pressure drop evolving with time. And then with that, we can see the mobility of these capsules. So the important dimensionless parameters of this flow, of this capsule flowing through a constriction are highlighted here. The ratio of the capsule diameter to the constriction diameter is important. Imagine if you have a very small capsule, it will just flow through the constriction without any resistance. But now if you have a very large capsule, you would need to deform a lot this capsule in order to make it flow through. The constriction ratio of the capillary, so what's the ratio, the diameter of the capillary to the diameter of the constriction. The surface capillary number, which is a ratio of, this is like a capillary number, but instead of having the interfacial tension, we have the force, the elastic force of the shell. So G is the modulus of the shell, and H is the thickness of the shell. So it's kind of like a capillary number, but now it's an elastic, elastic modulus that goes here in the denominator. So the more rigid is the shell, the lower is going to be this capillary number. So we can control this capillary number by controlling the rigidity of the shell itself. So Reynolds number and the viscosity ratio between the inner and the outer phase are important parameters. So we produce 5 different systems of capsules with varying the diameter and varying the shell thickness. And the goal here was to flow this capsules through this constriction and measure the pressure drop and see what happens. So here's an example where the capsule diameter is 44% larger than the capsule than the constriction. You can see that the capsule, we are injecting at a constant flow rate. So when the capsule reaches the constriction, the pressure goes up until the pressure is high enough to force the capsule to deform and go through the constriction. And then when that happens, the pressure goes down to the regular level. Let's call it this way. Okay. So here's just snapshots of the movie that I just showed you. showing the different levels of deformation of the capsule as time goes by. Now, the second video is the same systems in terms of rigidity of the capsule, but now I have a larger capsule. The capsule is 75% larger than the constriction, so you have a bigger capsule. The same thing, the capsule gets blocked. We're injecting at a constant flow rate. The pressure increases up to a point. I'll accelerate here a little bit. The pressure gets too high. But because of this capsule is larger, we're going to deform more and more, such that the shell cannot sustain that level of deformation and pressure. So this capsule will break. I don't know if you were able to see, it was pretty fast, but I have some snapshots here. So the capsule shell bursts, and then the inner content of the shell goes away. So in a sense, we have a capsule. It's something that we need to worry also now, is that we need to make sure that if we are trying to block a path of the water flow, we need to have capsules that can sustain the pressure drop that we are going to subject it to. So we could map in this diagram of the surface capillary number as a function of the size of the capsule. Conditions where the capsule can flow through the pore without being destroyed. So these are these red data points. And then you can imagine for the fixed capillary number, if you increase the size of the capsule, so you have larger and larger capsules, so they need to deform more to go through the constriction. It comes to a point that the deformation is so much that you're going to rip the shell. So then you get shells that are destroyed as they flow through the porous medium. So we need to produce capsules that are inside this red area of the plot. But if you want to use capsule as a target delivery of some agent inside the porous media, this could be a mechanical way of destroying the capsule. Then you would need to produce capsule in this blue region of the diagram. So in order to get a better hand on how to design or what's the needed elastic modules of the shell in order to get the right mobility, we developed a model, a numerical model to study this problem. So this was a PhD thesis of José, and we published this early this year. So the idea is that we have a single capsule that we're going to flow through a constricted channel, and then we're going to impose a flow rate. So try to mimic the experiments that we had, and then measure how the inlet pressure changes with time as this capsule flows through. So we use finite element methods to solve the differential equations combined with an immersed boundary method to describe the deformation of the shell. So I won't go into the details of the model here, but basically we are going to solve the Navier-Stokes equations for the inner and outer phase, and then an elastic mechanical equation to describe the shell deformation. And then we are using shell theory to describe this deformation. So here's just an example. So I'm going to initially everything is at rest. So the pressure is constant on the outer phase. The pressure in the inner phase is higher because the shell is already under tension. So it's like you have a shell that's already under tension. So you have an elastic force acting on that interface. So that creates a higher pressure inside, like a balloon. We are going to impose a flow rate. So there's going to be created a pressure difference, and the capsule is going to flow from left to right. You can see that, oops, I'm sorry. As the capsule is going to move through the constriction, the inlet pressure rises, as I'm showing here in this plot. And then as it flows out, the pressure comes back to the regular level. So we can measure how the inlet pressure needs to change in order to force a certain capsule to flow through the constriction. And also we can compute what's the tension along the shell, because then we can know if this shell is going to burst or not. So if this tension is higher than the maximum tension that the shell can withstand, the capsule will burst. So we can do that for different surface capillary number. So an infinite capillary number means that we have a shell that has no mechanical resistance. So basically we have just a fluid flowing. And so this is why on this continuous black line, there's no delta P. So the pressure doesn't go up for the capsule to flow through because there's no resistance to deform the shell. As the surface capillary number decreases, so the capsule is getting more and more rigid, so the elastic modulus of the shell is increasing. We can see that the pressure to force that capsule to flow through increases more and more. So we can map the ratio of the delta P of the continuous phase alone divided by the delta P, the maximum delta P that you need to flow that capsule through, as a function of the surface capillary number, basically as a function of the modulus of the shell, and also as a function of the size of the capsule. So this A bar is the relative size of the shell with respect to the pore throat. Okay, and as we expected, the more rigid is the shell. So we are moving to the left in this plot. So lower capillary number, the lower is this mobility reduction factor, because delta P max is going to go up. So I'm reducing the mobility of the water phase more and more. So the design concept here is that if we know how much degree of blocking we need, so we know this F parameter, we can design shell that's going to operate at a certain range of the surface capillary number. So that's our design parameter, how rigid the shell needs to be. So then the last part of the story was the master's thesis of Rafael. We want to see if the capsules were able to actually displace oil, the oil that was trapped inside a porous media. So in order to be able to see what was going on inside the pore space, we use confocal microscope. So the idea of using confocal microscopy to visualize flow in porous media was described in detail here by this paper by Sujit. So we made a porous media of sintered glass. So the pore throat was probably around between 180 and 200 micrometers. We use different dyes on the different phases in order to be able to visualize. So these dyes are emitting in different wavelengths, so we can see them simultaneously as we look at the image in the pore space. So so this is it's kind of like an alchemy that we need to play around here to match the refractive index. We need to have the same refractive index in order to be able to visualize and to get a 3D image of a confocal microscope. So we build these 2D stacks, and then we can construct the 3D images of the porous media. So in this example here, everything that you're going to see in the few next slides, the water phase is marked by this blue color, and the oil phase is marked by the red color. And the capsules are going to mark by this pink color. I don't know if you can see them, but they're going to show better in the next slide. So the basic idea is that we saturated our porous media initially with the water phase, and then we displaced the water phase by injecting the oil phase. And this is the final stage after the oil injection. So you have a porous media that is almost fully saturated with the oil phase. It's all this yellow. We have water as an irreducible water that's attached to the grains of our porous media, which are basically glass beads. And the irreducible water saturation here was 16%. Then we inject water to displace oil. And so after we inject water to displace oil, this is the remaining oil saturation was around 33%. So again, all this yellow regions are oil ganglia that were not displaced by the water phase. We inject
Marcio, can I just quickly ask you? So initially, is it water filled?
So we start, because we wanted to reproduce this irreducible water saturation. So we start with water and then displace the water with oil. So this is the stage that we get. The picture on the
top left there is already after the first displacement cycle, right?
Now, after the oil displaced the water.
Right.
So this would be like an initial condition of a reservoir. So you have water is not flowing. It's on its irreducible water saturation, and the rest is filled with oil. And now what we want to do is displace this oil. Okay. So here's after water injection. After we inject water, so we displace most of this oil, but we remain with the 33% saturation of oil. So we are injecting water and getting water on the other side. So this oil is trapped. It's not moving. Then we inject a slug of a suspension of these microcapsules. The microcapsules that we're injecting had a diameter of around 100 micrometer and a shell thickness of around 5 micrometers. So this more or less defines the rigidity of the shell. So the capsules, they flow in the water phase because they're suspended in the water phase. But as they are flowing through the water path, they're going to find pores that they are going to start blocking these pores. And then the water is going to have to flow towards oil-filled pores. So then at the end of the process, we get a remaining oil saturation of 26%. So there was a reduction of more or less a little bit more than 5%. So remember, it was an oil saturation of 33 that went down to 26. And here's the amount of oil that we produce from this porous media. So before injecting the capsules, we only get water flowing out because all the oil was not moving. And after we inject this microcapsule, we get this oil out. And so with this confocal microscope technique here, just to show the image, it's nice because now we can really visualize all the dynamics and the state of the phase distribution inside a porous media. So again, just highlighting the yellow are the oil globs that are trapped. The blue is the water phase, and then in pink there is the microcapsule. So we have different dyes in these different phases such that we can visualize them together. So as a final remark of this first story, we show that we can produce microcapsules with different diameters and different mechanical properties. And then we can control the mechanical properties. I didn't go in detail here in this talk by controlling the degree of cross-linking and controlling the shell thickness. We can get pore blocking by controlling these microcapsule characteristics. And then we need to specify the capsule design for different situations. So this is what we are still working now. So given a porous media, a pore throat distribution, what is the optimum capsule size that you need in order to get the right effect? And another big challenge on this research is how can we develop a large scale production of these microcapsules? You saw in the lab, we are producing milliliters per hour. If there's any hope of using this in a large scale oil production, there's no way that we could produce microcapsules using microfluidics. So the second story is the PhD thesis of Nicole. She's getting ready to defend her thesis. She was looking at pore-scale phenomena of a surfactant alternate gas injection. So it's well known that if you inject a gas as you're displacing a fluid, gas has a very low viscosity and very low density, such that you would create this viscous fingering because of the difference in the mobility between the gas and the oil phase. And the gas typically will flow towards the upper part of the reservoir because of the density difference. The same thing with water, but now water has a density that's larger than oil. So you have the viscous fingers also, and then water typically goes to the lower part of the reservoir. But now if you alternate a surfactant solution with gas, you can form a displacement front that's way more uniform, because when you're using gas to displace a surfactant solution, depending on the condition that you're operating, you may form a foam, and that foam will block the gas flow. So you reduce the mobility of the gas flow. So here's a very old paper from Holmes where they measured the gas permeability without foam. So you see a very high gas permeability. And now after they form a foam doing this surfactant alternate gas injection, the gas permeability with foam is orders of magnitude lower. There has been work already in this area looking at the pore-scale phenomena. This is from Lisa Biswall's group in Rice, where she was looking at foam formation in a porous media with different pore size distribution. So you have like a fracture, a more open pore region, and a very closed pore region. So what I'm going to show here, part of Nicole's research, she was looking at this process of displacing oil by injecting a surfactant solution followed by a gas injection. So we use this porous media here. This is a commercial porous media from Micronit. The porosity is around 57%, and the permeability 2.5 Darcy. So the procedure was that we first saturate the device with an oil, okay, which is the oil is dyed in this brownish color that you're going to see in the movies or in the pictures. And then we inject a 15 pore volume of an aqueous phase. This aqueous phase can be pure water or water with a surfactant. Okay, so we use the water without surfactant as a base case for analysis, and then we inject a surfactant at different concentration. And then we follow that injecting gas at a constant volumetric flow rate. and then measure the pressure, the inlet pressure during the gas injection, and visualize the flow dynamics. At the end of the process, we can use image processing to measure what's the oil saturation at the end of each of these steps. So this is an example of the state after injecting water. So the water phase is dyed with this pinkish color. So we are injecting water, we are getting water out of the micro model, and all this brownish are oil that are trapped by capillarity. So this oil is immobile. Now what you're going to see is that we're going to inject gas. So gas is going to displace the water. Let me accelerate this a little bit. So the gas first follows the easy way out, which is following the pores that are filled with water. So you can see that the gas is invading, following the pores that are colored in pink. As time goes by, I'm going to accelerate here. The gas gets to the other side, but as time goes by and the gas displaces this water phase, you're going to start seeing lamellas being formed in the gas phase. So you're going to start forming liquid films that will disrupt the gas path, and these lamellas will create extra resistance of the flow, and then that will divert gas towards oil filling pores. So as time goes by here, we start producing some oil, and then you see some states of lamellas being formed. So the idea is that as the gas displaces a surfactant solution, depending on the condition, that's what we're going to see, we can form a foam. This foam can be weaker or strong. So depending on the level of the foam formation, the pressure is going to increase, and then we displace more or less oil. So here are some images of this process. So this is the base case that we use for just for comparison. So in this case, the water had no surfactant. So in fact, it's like a water alternating gas injection. So this is the condition after water injection. Again, oil is this brownish color, water is this pinkish color. We inject gas for a long time until reaching steady state, and then we could measure what's the variation of the oil saturation. And here the variation was very small, was only 3%. So basically injecting gas didn't get any oil out, or very little oil out. Now we have a surfactant solution. So we increase the constant. This is the concentration of the surfactant solution. So after we inject gas, now we can clearly see all the lamella. You can see that the gas phase more here, closer to the outflow part of the model. You have all these lamellas here, because as the gas is displacing the water phase, you have all different mechanisms for foam formation, snap off or lamella breakout, and so on. So you have all these different mechanism of foam formation. And then once you have the foam is formed, you have a much stronger resistance for the gas flow. So you start pushing gas towards oil filling pores. And now after we reach steady state where we are not producing any oil, we see the variation of the oil saturation is 14%. So there was a quite increase on oil production. You can clearly see that in this picture here on the right, you have much less brownish area than the picture on the left. If we increase the concentration even further, so going from a 6.2 to a 15.5 concentration, you can see that there is a lot of lamella formed because you have a higher concentration of surfactant. You form a stronger foam, and now the variation of oil saturation is even higher, it's 21%. Okay, so we are able to really displace oil, but by having this foam formation. So here in the left is the pressure, the inlet pressure as a function of time. The black curve is when we inject gas displacing just the water phase without surfactant. So the pressure goes up as we are displacing the water phase, and it comes to a point you reach a maximum and then it flows down. If we increase the concentration to 6.2, you see that the pressure goes up. The maximum value is higher than what you get when you're displacing just the water phase. So this is associated with the formation of the lamella. The foams that the lamella that you're forming creates a stronger resistance for the flow. After you reach a maximum value, it will go down. And so the maximum pressure is higher, but the final pressure is lower because you displace more oil. So now you have more path for the gas, so that's why it's lower here. If you increase the concentration, the same thing continues to happen. The maximum pressure is higher, and then it goes down to an even lower pressure. So you see that controlling the surfactant concentration, you get this higher injection pressure. That's why you displace more oil, because you're pushing oil towards oil-filled pores. You get a stronger mobility control, and then a more efficient oil displacement.
It's all at constant flow rate, right?
Everything at constant flow rate, yes. So as final remarks for this small story here is that the gas foam films are formed when you're displacing the surfactant solution with the gas phase. And again, as these lamellas are moving, you get a stronger flow resistance. So the pressure behavior is not only a function of the surface tension. I didn't mention this. These two values of concentration that I'm showing here are already above the CMC of the surfactant solution. So we are way above the CMC here. So it's not only a matter of the interfacial tension. The concentration of surfactant becomes important in this foam formation. And the last story, again, looking at pore-scale phenomena was the PhD thesis of Paula. She recently graduated, and she was studying condensate blockage mitigation by wettability alteration. So she was looking in general of condensate gas flow, but the difference that I add this story here is that the two first previous research that I was showing, they were more experimental than theoretical or numerical. This is really a pore-scale flow model. So it's a modeling simulation type research. So Paula published, the things that I'm going to talk about here are described in these two papers. So the idea is that if you have a condensate gas reservoir, if the pressure is high enough, you're probably going to be in a point like this, where your fluid is in a gas state. If you start producing that reservoir, the pressure will go down, and as the pressure goes down, it may cross the dew point of that fluid system, and as it crosses the dew point of the fluid system, you start forming a liquid phase. And as this liquid phase is formed, it may block the gas path. So it's well documented in the literature in production of condensate fields that as you start producing, it comes to a point that the gas mobility is drastically reduced and your gas production falls abruptly. So one way that's discussed in the literature to try to avoid or mitigate this problem is changing the wettability of the reservoir near the well production, where the pressure is lower, where you see more of this condensate blockage. So this is what Paula was looking at in terms of pore-scale modeling. So the question is, what happened if you change the mobility of your grains such that now your liquid condensate is not wetting the grains? So how does the dynamics change, or how can you improve the gas mobility? So Paula developed a compositional pore network model. So it's a regular pore network, but now we need to solve the thermodynamic, an equation of state to determine what's the saturation for a given pressure and temperature, what's the liquid and gas saturation, and what's the composition of this gas and liquid phase, such that we can compute the properties of the system in each pore throat, because that will affect the mobility. So we have a network of nodes and edges. The throat or the edges are represented by a converging diverging channel. This is important such that we can include in an effective way the capillary effect that we get once you form a liquid bridge that's blocking the pore throat. So we have just a regular network model with nodes and edges. And what's important that the gas flow and the liquid flow through each of these capillaries is going to be a function of the mobility of each of this phase. So the flow rate is going to be the mobility times the pressure difference. And now, so we need to model adequately the mobility of each of these phases. Okay, the example that I'm going to show here was done with this fluid composition. So there were carbons from C1 to C16 at different proportion, and also we had CO2 here. So it's very important. The whole physics is in this equation here. How can we describe the mobility of these liquid phases, and how does that change? Because that's going to control the dynamics of the flow. So if the let's look at first if we have a liquid wet porous, which was the previous work, the first work that I showed you. So if the pressure is below the dew point, we are going to start condensing liquid. So if the liquid is condensed, if the saturation is small enough and the liquid phase is wetting the grains, you're going to form a film that's going to be attached to the wall. So you have a core annular flow. So you have liquid flowing through this thin film and gas is flowing through the middle. Because of you have this annular flow, the velocity of the gas is going to be much higher than the velocity of the liquid. The liquid is flowing as a thin film attached to the wall. So you have this viscous resistance for the flow of the liquid, and the gas is flowing much higher at a much higher flow rate. So you're going to accumulate liquid. Okay. So as you accumulate liquid, it's going to come to a point that you build up enough liquid phase that this core annular flow becomes unstable, and you can have this snap-off phenomena. Once you have a snap-off phenomena, the liquid phase, you form a liquid lens that's blocking the gas phase. So at this condition, the gas mobility is zero. The gas is not flowing through. If the pressure difference in the pore throat is strong enough to displace this liquid lens because there is a capillary resistance up to that. So if the pressure difference is smaller than the capillary threshold, this will remain blocked and the gas mobility is going to be zero. Is the pressure difference that you're computing as you're computing the capillary network model is high enough, you're going to displace that liquid phase, and then you go back to a situation like that, a core annular flow. And then you typically oscillate between these two flow states. So you form a lens, the pressure will build up, and then you displace that lens, and then you keep oscillating that. Now, if you have a gas wet porous media, when you start forming a liquid phase, the liquid phase will not spread through the wall. So you have what's called this dropwise condensation. The liquid condensation gets higher and higher as you form more and more liquid. And now a very important difference occurs. Because you have this drop that spans throughout the cross section of the pore throat, the liquid and the gas phase will flow with the same velocity. So you don't have that core annular flow pattern. So you don't have that liquid accumulation because of the difference in the velocity of the two phases. So we implemented that on the pore network model. And the goal here was to see what's the effect of changing the wettability of the porous media. So we tried different wettability and compared with the original, let's say, completely liquid wet porous media, which would correspond to a contact angle of 0 degrees. So we fixed the temperature, and then we changed different pressure levels. So all these pressure levels that we try are inside already the two-phase part of the diagram. So they're below the dew point. So there is a liquid and a gas phase. As we decrease the pressure, it's important to keep that in mind. As the pressure is getting lower and lower, it means that the liquid saturation is getting higher and higher. So we are moving in the region of the two-phase diagram that you're increasing the liquid saturation. And we change also the velocity of the flow. So basically the pressure difference that's acting on that porous medium. And the way we are going to quantify the effect of the wettability change is by this improvement factor. So we create our model. In a sense, we run like Darcy experiments. We inject at a given flow rate. We measure the pressure difference. We can run this with a completely liquid wet porous media, and then we get a permeability of the gas, what we call here an untreated rock. Now we run the same thing by changing the wettability of the porous media, and then we can get the permeability of the gas of the treated rock. And then we measure the ratio between these two. So ideally, we want this number to be larger than 1. We want to increase the permeability of the gas phase. We want to produce gas. We want to avoid the gas blocking effect. So this is what's highlighted here. If IF is larger than 1, this is good. This is flow improvement. If IF is less than 1, this is bad. We are even impairing more even the flow. So what these diagrams here are showing is that, so in the vertical axis is what we call here from Q1 to Q7, it's increasing the velocity of the flow. As we are increasing the velocity of the flow, it's becoming easier and easier to displace trapped liquid phase by capillarity. And we change also the pressure of the flow. Remember, lower pressure means higher liquid saturation, higher pressure means lower liquid saturation for different contact angles. So this is the scale. So greenish is, I'm sorry, this light blue is 1. So everything that's green, yellow, or red is good. Everything that's dark blue is bad, okay? So what the results are showing here is that if you change the wettability too much, this is not good. So if you have a very non-wetting porous media, you get all this blue, which is basically you're decreasing the gas mobility even further. And then you can get an optimum operation, which would be this red. If your contact angle is near 90 degrees, which makes sense, because if you have a 90-degree angle, you're basically turning off capillarity because there's no curvature of the meniscus on the pore throat. And then you can even see what's the optimum flow rate that you need to operate in this condition. So again, I think this is a good example that understanding the pore scale physics can really help design processes and help understanding the real physical mechanism that's occurring in all these complex porous media flow. So with that, I'd like to thank your attention. I'll be glad to answer any question. I need to thank the people that actually did the work. So the work that I showed here are these that have these white balloon around them. And also need to thank the funding for the porous media research in our group. Thank you very much for your attention, and I'll be glad to answer any question.
Thank you very much, Marcio. Do we have any questions from the floor? If we do, please